Hello and welcome to my presentation on the history of math, part 4. In this era of intellectual revolutions, two figures stood out as the founders of calculus. Newton's approach to calculus would use a synthetic method of fluxions and fluents, and they were based off motion, such as a fluxion was a derivative and equivalent to velocity, and a fluent was a thing that changed over time, equivalent to acceleration. He revolutionized physics with his different laws of gravity, motion, and much more. In addition, he founded the power series and created an infinite generalization of the binomial theorem. Gottfried Leibniz was also a founder of calculus, and his version was much more similar to our own, and it was based off differentials and integrals, and it used the concepts of sum and difference, as in that's what the symbols that we still use today are based off, like the d in a derivative stands for the Latin word of difference. In addition, he invented modern calculation rules like the quotient rule, and there was this big argument over who founded calculus. Was it Isaac Newton because he created the idea first, or was it Leibniz because he was the one that published it first? In the end, Gottfried quote-unquote won, because that is the version that we use the most. We could not go any further without talking about Leonhard Euler, the greatest mathematician of the 18th century, for his work in various theories, such as the theory of differential equations, multivariable calculus, variation of calculus, and number theory. For instance, he formalized multiple integration and many other techniques like integration by parts and double integrals. In addition, his number theory is where he dominated and extend the works of Fermat's theorems and work particularly in residuals, or in the modern terms, remainders. He also published some very influential textbooks that defined math concepts, specifically of the notions of sine and cosine, and overall he kind of invented trigonometric calculus. Interestingly, his textbooks had no geometry and were only analysis, and this represents the gradual change and emphasis on the study of curves to the study of analytical expressions involving one or more quantities as well as constants, that is, functions of one or several variables. So we're taking a step away of the forefathers that tried to relate area and tangents. In addition, he was able to develop a general theory that you could determine a curve y that maximizes or minimizes an integral of the form seen on the right. He used a polygonal approximation for this process. The driving force of development in calculus in the 18th century into such things as partial derivatives or double integrals and such were physical problems, such as the brachistome problem, where you have to determine a curved path that a ball descending under its own weight must pass from A to B in the shortest time possible. Supposedly, Isaac Newton was able to solve this in only 12 hours. There were many calculus books first being published in this era, and some of the most influential were created by Maclaurin, who was known most for his series that allowed him to use it for the second derivative test for extreme values like max and min. His book was in response to criticisms of the foundations of the theory of fluxions voiced by George Berkeley, and it was quite extensive but kind of boring. Another great mathematician of this era was Joseph Lagrange, who, in addition to his work on the calculus of variations, attempted to eliminate all reference to infinitesimal quantities or even to limits, and to base the entirety of calculus on the notion of a power series. In this brave but pretty foolish attempt, he created the term derivative, since the p term in his series is derived from f of x, and he found a new way to look at the fundamental theorem, but it was all false, based on the false assumption that all differential functions have a power series. Algebra in the 18th century there was not much general innovation, but it was focused on improving and making general procedures for such things as solving polynomial equations. Many of the mathematicians that I discussed before contributed greatly to these topics. That includes Newton, Maclaurin, Lagrange, and Euler. Maclaurin talked about topics such as the manipulation with fractions, powers of binomials, roots of polynomials, and etc. A standout was what he called a general theorem for eliminating unknowns in a system of equations. This method today is what is known as Cramer's rule. Lagrange talked about many of the same things, but he featured a unique way to solve polynomials with permutations. He uses transmutation that gives an introduction to the idea of permutation of the roots of an equation. This is a very important part of the math in the following century. Finally, Euler advanced the understanding of a rank of a series of equations and showed that for a system of n by n equations, there does not necessarily have to be a solution. Now we can discuss the Lovecraftian horror of non-Euclidean geometry, a topic that led man to madness. At this time, geometry was connected both to algebra through the relationships under the term analytic geometry, and to calculus through the application of infinitesimal techniques to the study of curves and surfaces, such as those used by Newton and Leibniz in their attempt to bridge the old topics of area under a curve and tangents. However, there are those who try to perfect Euclid's work and expand upon it, specifically Euclid's fifth postulate, or the parallel postulate, that asserts that through any point not on a given line, there's exactly one line that can be drawn parallel to the given line. One of these men was Girolamo Saccharici, who tried to prove the postulate by contradiction, but stopped when he could not disprove his hypothesis of acute angles, that basically for a triangle made up of two right angles and two acute angles, it had the ultimate result of showing that the sum of angles of any triangle is less than 180 degrees. He was so disgusted by this obviously wrong idea, he gave up. Lambert tried to continue upon his work, but found that he could also not necessarily disprove it, although he did make the very important discovery that larger area means a smaller angle sum, and ultimately concluded that, based off the inverse theorem, the hypothesis of obtuse working for spheres, the hypothesis of acute holds for the surface of imaginary spheres. This would eventually lead to the study of non-Euclidean geometry. We shall end this presentation about the time of great intellectual revolution by talking about the various ways that mathematics was applied in this century, specifically probability. One of the important mathematicians in this field was Abraham de Moivre. De Moivre found new ways of calculating probabilities, such as finding how many trials it would take to have a 50% of winning, but most importantly, the normal distribution. He did this by applying his knowledge of series to develop the curve and some of its properties. This curve is incredibly important because it allows statisticians to model normal systems like human height that tend to be more focused on a mean value. Of the many applications was measuring errors, such as for astronomy or in mathematics where there are many unknowns. There's also the applications in the field of finance, such as annuities, in which an individual would give up a certain amount of money to get paid another amount of money, such as you give $50 and you gain $1 back for the rest of your life. It was used to calculate the cost-risk analysis of it. Is it worth to even do it in the first place? And finally, it was used for lotteries and gambling. Thomas Bay was also an important figure in the field of probability and statistics, for he was the only one to attempt a direct answer to the question: is it possible, given empirical evidence, that a particular event happened a certain number of times in a given number of trials? What is the probability that this event happens in general? Such as, if I pick up 3 white balls from a bag, what's the probability that I get a red and a white ball next time I pick?